Some more properties of determinants. Last class we learned how to calculate the determinant of a 2 by 2 and also how to do it for 3 by 3 matrices. And as a warm-up, we have these 5 questions, and these 2 by 2 matrices are all somewhat related. And when you do the determinants, this one's 4 minus 6, which is negative 2. This one is 16 minus 24, which is negative 8. This one over here is 8 minus 12, which is negative 4. This one here is 6 minus 4, which is 2. And this one here is 8 minus 10, which is negative 2. So they all have, well, some of them have the same. Notice how number 1 and number 5 actually had the same answer. And just some other things to kind of notice, for instance, that number 4, the original matrix, is the same numbers as number 1, but the rows are swapped. And these are just some things that we're going to see is if we know the answer for one determinant, for instance, if we knew this answer, is there some kind of shortcut that would enable us to answer questions like 2, 3, 4, and 5 without having to start from scratch? And that is the topic of today's lesson. So for the first rule, rule 1, which is if you swap rows, what happens to the value of the determinant? And we saw this in the warm-up where this equaled negative 2, but if we swap the 2 rows, 3, 4, 1, 2, after swapping the rows and recalculating the determinant, we get positive 2. And this is going to be a rule. If you swap any 2 rows, the determinant is negated. So a test question is something like this. If I tell you here, if I say given that the determinant of some matrix A, B, C, D is 9, and then the question would be, what's the determinant of C, D, A, B? What do you think the answer would be? And yes, it's negative 9. If I have a 3 by 3, if the determinant of that is something like 6, and if I swap 2 rows, it becomes negative 6. But if I swap 2 more rows, it will be negated again and go back to the original. So this is rule number 1, though. Swapping rows negates the determinant. You could actually prove that and kind of see why that is, but I'm not going to do that right now. Actually, I will do it. That's the determinant of the original, whereas when I swap the 2 rows, I get CB, or I'll call it BC, minus AD, which is indeed negative AD minus BC. So that's a little proof of it, at least for the 2 by 2 case. These other rules are not going to prove, but you could prove them in similar ways. Okay, rule number 2 is how the determinant is affected when a row is multiplied by a constant. And notice how rule number 1 is kind of like based on row operation number 1, and rule number 2 is kind of based on row operation number 2. We see this a bit in the do now when we compared the determinants of 1, 2, 3, 4 with the determinants of 2, 4, 3, 4. This one was negative 2, whereas this one was actually 8 minus 12, which is negative 4. The determinant got doubled, and this is generally going to be the case, or always going to be the case, if a single row is multiplied by by some constant, then the new determinant is also multiplied by that constant. So a test question would be, if you're given that ABCD equals 9, then what would the value of 3A, 3B, C, DB, and the answer is going to be 3 times 9, which is 27. There are two kind of corollaries to this. One is that if I multiply one row by one thing and another row by another thing, that should be 2 times 3 times 2 times 3 times 9, which is 54. And what confuses some people is when there's a number all the way out here, or let me write it this way, determinant of 3 times the matrix A, B, C, D. That's kind of like saying the determinant of 3A, 3B, 3C, 3D, which is not going to be 3 times 9, but it's going to be 3 squared times 9, which is 81, because each row got multiplied by 3, and that's something that confuses some people. Now there are 3 row operations, so there's likely to be 3 rules. So rule number 3, which is rule number 3 is when row operation number 3 happens. In other words, I have matrix 1, 2, 3, 4, and I apply row operation number 3. I take, for instance, if I do row operation number 3, I do 3R1 plus R2 and replace row 2 with that, and I get the matrix 1, 2, 5, 8. Well, if you work out the original determinant, which is -2, and you work out the new determinant, you'll notice it becomes 8 minus 10, which is also -2. So the rule, the third rule for determinants is if you do row operation number 3, the determinant remains unchanged. So if you add to a row a multiple of another row, the determinant does not change. So an example of this is if I say ABCD equals 9, and then the question is, what about AB 5A plus C, 5B plus C? That is also going to be 9. Because the only thing I did was row operation number 3, which does not change the value of the determinant. Besides these sort of little test questions that could come up, there could be one use of this is, suppose I have a 3 by 3 matrix, 1, 2, 3, 2, 1, 4, 3, 1, 5. And it's annoying to do the determinant of a 3 by 3 matrix unless one of the rows has some zeros in it. So one thing you can do is you can do row operations. For instance, let's say I wish that that thing was a 0, so I can do -2 row 1 plus row 2 into row 2, and I would get 1, 2, 3. The last row would not change, but the middle row is now -2 plus 2 is 0, -4 plus 1 is -3, and -6 plus 4 -2. And now that I have a 0 here, I can expand by column 1. So I get, anytime I'm doing an odd column or row, I'm going to alternate plus, minus, plus. So plus 1 minus 0 plus 3. And 1 is going to go, if I remove the row and column that 1's in, what remains is minus 3, minus 2, 1, 5. This one I don't have to worry about at all, so it saves me a little bit of time. And if I do this 3 here, if I remove that, the row and column that the 3 is in, I get 2, 3, minus 3, minus 2. So this saves me a bit of time. Minus 15 minus negative 2, which is plus 2, which is minus 13. That we don't need. And then plus 3 times minus 4 minus negative, which is plus 9, which is 15. I get 2, which is the answer. And it's arguable whether doing a row operation and then, and very important, determinant does not change. Does not change when you do row operation number 3. On the other hand, if I use any of the other row operations, let's say my matrix was 2, 4, 6, 2, 1, 4, 3, 1, 5, and I decide, I really want to make a 0, but it's not easy to make a 0. I'm going to first have to do row operation number 2, half row 1 into row 1. Well, when I do that, 1, 2, 3, 2, 1, 4, 3, 1, 5, what's happened is that the determinant has actually changed values by multiplying a row by a half. The determinant got multiplied by a half also. So I'm going to need to sort of counteract that by multiplying this answer by 2 because it's been reduced. I showed you before that this matrix becomes 2. I'll remember if I do row operation number 3 by turning that thing into a 0, I end up with what I had before, minus 2 times this plus that is 0. Minus 2 times this, that's minus 3, that's minus 2, 3, 1, 5. And when I expand, I do end up getting 2 times 2. It was minus 13 plus 15, I think, equals 4. So you do have to be a little careful. If you do row operation number 3, the determinant does not change, but if you do row operation number 1 or 2, you have to be careful, remembering that if you do row operation 1, the sign swapped, unless you do an even number of swaps, then it stays the same. And if you do row operation number 1, whatever, you're going to have to balance that out by whatever factor the determinant changed by. Okay, that's it for this lesson.